Welcome, everyone. My name is Brett Peterson. I'm the Director of Sales and Operations for North, Central, and South America here at Isograph. Thank you for joining us today. As a point of introduction, Isograph has been creating and improving software around the world for over 32 years. Our headquarters is based in the UK, and we have a beautiful office here in Alpine, Utah. Now, I'd like to introduce you to Joe Beland. He'll be conducting our presentation today, and he's our lead technical support for North America. And Joe's been with Isograph for over 16 years and worked with thousands of organizations helping their employees become conversant with our software tools. Now today, Joe will be giving a high-level overview of one of our flagship products, our gold standard product, and it's called FaultTree. And so he'll be covering that module today. Now, if you have any additional questions or you'd like to look into, our training, I wanted to post some of our contact information here. And you can contact any of us, Joe, myself, and my sales manager is also on the call, Clint Armistead. So feel free to definitely reach out for additional questions or any additional training that you might need on our FaultTree tool. So with that being said, I'd like to turn the time over to Joe to run through our product at kind of a high level. It's very simple, very easy to get started. And so let me share that screen, Joe's screen, right here. And momentarily, you should be able to see this come through over to Joe's screen. But we really appreciate everyone attending today and hope that, this gives you a really good foundational piece to start out with on our FaultTree tool.
Thanks, Brett. I'm sharing my screen. I hope you can see the Reliability Workbench with the FaultTree module showing.
Yeah, it looks great.
Okay. Yeah, so as Brett mentioned, the FaultTree Plus was actually Isograph's very first product released in 1986. It's been continually developed and improved ever since then. So it's probably the most mature FaultTree product on the marketplace today. Anyway, I was just going to take you through a quick overview on how to build a FaultTree, how to use the software product, and some of its features. So let's take a look at it. First, I have a completed FaultTree here, and when we look at the results, we'll use this one for looking at the results. It's a very simple to use product. I can build the FaultTree, and I'll take you through that in just a moment, enter failure data, and then run an analysis to get the results. Those are the three main steps I want you to keep in mind while we build a FaultTree. This particular FaultTree project is modeling a cooling system, and I'll take you through building another much simpler one. The cooling system, there's mechanical and electrical components that would lead to the hazard, the total loss of cooling top gate. So again, if you're not too familiar with FaultTrees, we always start with a top event, a hazard, something that's bad that we want to avoid, and we want to know how likely it is to occur. We want to know what faults can combine and propagate through our system to cause that hazard to occur. In this particular case, we have a total loss of cooling as the hazard in our system. This is a protection system, a cooling system for a reactor vessel. The top event is created by combinations of basic events. These symbols down here are those basic events that their occurrence can lead in certain combinations to that top gate. The combinations are determined by the logic of the gate. These gates, or excuse me, the logic of the FaultTree, these gates that we have throughout the FaultTree, their symbol type indicates the combinations of faults that lead to that top event. So this symbol right here is an AND gate. It means both of these things have to occur in order for this thing to occur. This is an OR gate, meaning any one of the occurrences of these things could cause the output. So we'll start by building the FaultTree from this sort of deductive backwards approach. We start with our hazard and work our way down. So let me build a new FaultTree to show this process. Click the button right here to add a new top gate to my FaultTree project file. So this top gate right here, this will be my hazard. This will be for let's build a very simple protection system. The safety system fails when it's needed. So safety system fails on demand. I'll call it the PFD, probability of failure on demand for my safety system. On demand, okay. We're going to set up some of these other properties for this gate later on. But first, I'm going to start by building the structure for this FaultTree. Safety system has a few elements. It has sensors to detect unsafe operating conditions. And so the sensors failing could lead to the failure of the safety system. I'll add a gate because there's going to be logic for those. There's multiple sensors, and they have to fail in a particular logical order. I have valves, so some shut-off devices that stop the process if it's unsafe. So I'll add another gate for the failure of those items. And then there's also a logic solver. And so I'll add a basic event. So I click on this button on the toolbar to add basic events. And so this will be my logic solver. For my sensors, I have 3 sensors. So this was my sensor gate. I'm going to be putting text to everything in just a minute. I'll add 3 basic events. So I can just keep on clicking when I'm in add event mode to add additional events. And I have 2 shut-off valves for the system. Okay. Let me go back to clear add mode. Now I can click on these things to be able to edit them. You can either double click on them to edit the gate. So this is the failure of the sensors. Sensors fail. And we'll say we have 2 out of 3 voting logic, meaning we need 2 of those 3 sensors to be working correctly. So I'll set the gate type to vote and enter a vote number of 2. 2 out of 3 sensors fail. Another way of editing the information is with the diagram and grid option, view mode option. This gives me a little table at the bottom. It sometimes makes it easier to enter data. So I can say, let's look at my gates for this system, and I can click on them to be able to enter their text information rather than going through the program dialogues. So I'll be using this from now on. My final gate was for my valves, so valve failure. Or valve system fails might be a better description for that one. Okay, and I can do the same. Oh, and this will be, by the way, an AND gate. So I can just double click on it where it says gate type and change it to an AND gate. Okay, that means both valves have to fail to shut in order for the safety system to fail. So let's enter the basic event information, so just some descriptive text for those basic events. So let's see, here we go. Here's all my basic events, and I'll just go through and give them names really quickly. So this is my logic solver failure. Now, in a real fault tree analysis, I'm doing this a little bit on the quick side. In a real fault tree analysis, I don't always want to give good, complete descriptions for everything. Describe the failure mode, describe the failure cause. So from a real perspective, I'm not doing the best possible job I could with this fault tree. I always want to be a little more descriptive on the information. So this other event here, EB4, is one of my sensors. I'll put this as sensor 1. Now I'm going to do something here before I get to these other 2 events. Sensor 1, so all 3 of these events are the same. So what I'm going to do is I'm going to edit sensor 1 right here and enter some failure information for it. So that's the second part of a fault tree. There's a qualitative aspect to it, that's drawing the fault tree diagram, representing the failure logic. And there's the quantitative aspect, inputting numbers to be able to calculate a failure rate. So, and that's handled through the failure model. So I can enter the failure model for this basic event. Let me create a new failure model. This is where I can put in failure data. There's several different failure model types to choose from. It's a little bit daunting at first, but most users will stick to 2 or 3 that are specific to their industry. So I'll give you a few ideas of how that might work. The fixed models, where you know a fixed probability of failure. The rate models, where you have a failure rate and repair rate. MTTF is similar, but you have a mean time to failure and mean time to repair for the component. Dormant is used in, usually we see that in protection systems, standby systems. That's likely what I'll see here for the valves. We'll use a dormant failure. If you're in aerospace, you'll probably be using the time at risk model a lot. That's where you have an exposure time for certain component faults. You know, certain components on an airplane, they're only at risk of failure during specific phases of the flight. For instance, your landing gear is only at risk of a failure during the takeoff and the landing of the aircraft. You know, when you're cruising at 30,000 feet, it's not doing anything, so you don't consider it as a fault. Then we have other ones such as the IEC 61508 model. I probably also use that in a protection system such as this. We see this in process safety as well as automotive, when we're looking at dormant faults and protections. Okay, and so that's a few of the most common ones, and then there's also a lot of special cases that I don't really want to go into too much detail on all of these right now. So for the sensor system, I'll just use a simple MTTF model and say how often does the component fail. Let's say there's the MTTF for each sensor is say 5 years, and it will take let's say 12 hours to fix one of the sensors when it fails. I'll select OK to add that failure model. And I can select OK again, but before I do that, I want to show a few of the other options we can set for events. We can set the appearance, change the color, change the fonts, and add additional notes, any extra comments or text we want to embed in the event so we can find out more information about it, and also even hyperlink to external documents or web pages that contain more information about this particular item, whatever it happens to be. Okay. Now that I've selected it, now these other two sensors are identical, right? So I don't want to have to redo all that effort for the other two, so that I can simply duplicate this one. Let me get rid of these two events. I can just simply delete them. And then I can duplicate this by selecting copy and then paste special to create a new item with the same properties as the first one. I can do it again to create 3 sensors, all with the same failure data. Notice the gate changed types again while I was doing that, so let me set it back to that vote gate. Okay, and I can do a similar thing for the valves. Let me just figure out those last two. Valve failures, valve 1 fails, and edit its failure model. This one will probably use, say, a dormant fault. Valve fails, failure rates 0.001, 0.1 failures per year, MTTR of 24 hours, and we test it since it's a dormant fault. We have to test it to see if it's still working, and maybe we test it every month. So 0.08333 is 1 month in units of years. Okay, so I've entered failure data for that event. I can actually reuse again, I'll do that same thing, copying and pasting the event to create the second valve. And I'll do one more thing for the logic solver, adding its failure rate as well. I'll just add this in so we can get some information for this basic event. Say failures are 1 per 50 years, and repair rates of 70. Excuse me, this is failure repair rate per year, so 0.001. Excuse me, I'm getting my units confused. Let's say 100 repairs per year. That's about 3.5 days or so to repair. Okay, so that's the basic process of building the fault tree. You add the gates and the events to describe the failure logic. So in this case, we have a safety system, which consists of 3 basic systems or subsystems, a sensor subsystem, a valve subsystem of the actuators, and a logic solver. We've described the combinations of faults that would be required to disable each one, 2 of the 3 sensors failing, or both valves failing, or the logic solver failing on its own. So we've described all those different possible failure paths. And then we've entered failure data, describing how often and how long it takes to repair for each item. And from there, we can run the analysis and get some results for this one. We'll look at both this one and also for more robust answers, we'll look at that cooling system we had earlier. So to perform the analysis, I'll click the green traffic light. Ideally, I'd first go to the project options, and there might be a few options such as system lifetime that I might want to set. But I've already predefined all those options for now. System lifetime is the period of time over which we want to analyze it. I ran the analysis. It says analysis complete. I go to look at the results summary, and we can see for our safety system what we expect the probability of failure on demand to be. That PFD, or Q, is the unavailability. That's what that symbol there represents. The unavailability of the safety system is 2.198 times 10 to the negative 4. We expect a failure about every a little more than once per 5 years. Excuse me, a little more than once per 50 years. I'm reading my numbers wrong. An unreliability is about a 20% chance of experiencing a failure over the lifetime, which is a 10-year life. And we have other calculations for downtime. Unavailability, this one isn't relevant to this particular system. This is an aerospace measure, unavailability per flight hour. So we get a range of different results. Depending on the type of system, we might be looking for different results in terms of the PFD, probability of failure on demand. We might be looking for a frequency of failure, how often it occurs, or an MTTF. In this case, I've turned those calculations off for this particular system. We can also view cut sets. Cut sets show the combinations of faults which will lead to a system fault. So we see the logic solver, the 2 valves, the sensors, and combinations of the sensors. And we can also view the importance analysis. And the importance analysis tells us which event is most likely to be involved in a system fault. So the logic solver has the highest Fussell-Weasley importance, meaning about 90% of the time when the system fails, it's due to that logic solver. It's the Fussell-Weasley importance essentially represents how likely that event is to be involved in the fault of the system. Let me go back up to our other system, our total loss of cooling system, and just show you some of these other more advanced features for the results summary. I'm taking a look at this specifically for the cut sets analysis. One of the things I can do with the cut sets analysis is find those combinations of faults. I can look through my event list. Firstly, if I don't understand what those symbols, the IDs represent, because they're abbreviated in this case, I can click the details button. It'll give me the event description. So if valve 1 is stuck closed, pump 2 primary fault will lead to a total loss of cooling. I can see how that would work in the fault tree by selecting the cut set, selecting trace sets, and it will highlight in red the path down from the top gate to the individual basic events that make up that cut set. So we can see how those two component faults, those two basic event faults, combine and propagate up the tree to produce the total loss of cooling hazard. So valve 1 is stuck closed, which causes the failure of valve 1 to be closed, which causes a loss of cooling leg 1, combined with the primary failure of pump 2. Pump 2 is now unavailable, causing loss of cooling leg 2. The combination of those two together, loss of cooling leg 1 and 2, causes there to be a loss of cooling to the heat exchanger, which causes a loss of cooling, total loss of cooling in our system. Okay. Clear that trace to return my fault tree to normal. Okay. Brett, is there anything else you'd like me to go through in the fault tree?
I think Clint had a question for you.
Sure.
A couple of things I was wondering about, Joe, or having you show, is how this particular, how FaultTree can be converted to other modules that we offer.
Sure, yeah. So that's one of the advantages to the Reliability Workbench is it's an integrated suite of products. I've mentioned our FaultTree is our flagship product, but we've built up a suite of supporting products over the years. So if I select the module selector, you can see those other supporting products. And the nice thing about Reliability Workbench is there's linking between all these different modules. So one of the main ways that could be linked is in terms of the failure rates. So I talked about creating those failure models and entering failure data into the system. So that's one of the first places that's hard to get started for many people, is they don't know the failure rates. Well, one way of getting at that is the prediction module. You can jump into the prediction module, and this is specifically for predicting failure rates for electronic components using a number of prediction standards. If you've created a project here and figured out some of those failure rates, there's a very easy function to convert your prediction data into a fault tree. There's also a data linking feature that allows you to create data links between that prediction and that fault tree. So if you make changes on the prediction side, you can easily update your fault tree failure rates with the latest data from the prediction module. Another way of getting that failure data I'll mention is our parts libraries. We've built in two popular parts libraries. The second to load is a massive database. The IAEA, which is an International Atomic Energy Agency library, and the NPRD, which is the Non-Electronic Parts Reliability Database. We've built both those libraries into the tool, and they both also contain failure rates information. And you can, it's as simple as, I can select one of these components. It's as simple as dragging and dropping it into the project to create a new failure model from the data in that library. Does that answer
Joe,
your
I know
question?
we don't have a lot of, I'm sorry, I know we don't have a lot of time today, but can you discuss just at a high level how event tree ties into fault tree? And then a lot of our customers come to us with spreadsheets where they've built out some of this stuff. Can you discuss like the importing and exporting feature of the tool as well? And that's all I have for now.
Sure, absolutely. Yeah, so the event tree question, that's a separate webinar, I think, on its own, but I'll just talk about the links to the event trees. Fault trees and event trees are very closely linked. Our original tool, the probability risk assessment tool, which Isograph first developed for the nuclear safety industry, they rely very heavily on event trees quantified with fault trees. So the hazard occurs, that total loss of cooling occurs here, or maybe my safety system fails on demand. But that's not all there is to the story. There's other hazards or faults that go along with that. Safety protection system only produces a bad consequence given the occurrence of some unsafe reactor condition. And that's where we might build a fault tree, change this view over, to show the possible consequences from a bad occurrence. So a temperature surge occurs, and based on the status of our cooling system, that can lead to different consequences. Oops, let me turn on the view to make some of the view options to make this a little more legible. It shows the failure and success of the different systems. So the way that these are linked to each other is that these event tree sequences, the columns and the success and failure branches within the event tree, can be linked back to fault trees. So this cooling system here is linked to my fault tree cooling system, and therefore the branches are quantified by that fault tree. Okay, so that was the first one, and the second one was about the imports and exports. So there's a fully featured import and export tool to allow you to put data into or export data from the software, the Reliability Workbench application. We can import and export to Access, Excel, XML files, text files of any type. So this is a really popular way of inputting data. Again, nobody wants to have to type in all their failure data. If you've got 100 components, you don't want to have to type in 100 different failure rates. If you have a bill of materials in an Excel spreadsheet, just go ahead and import that. You can import a spreadsheet. If you have a list of all the events, all the components in your system, you can import that events list. You can even go so far as importing the fault tree. That gets a little more complicated because you have to somehow define the connections and the relations between everything. And that's a little bit harder than just a list of items. Now we have to link them all to each other. But even that can be done, and we even have special features for importing certain fault tree tables. If they're formatted in a certain way, we have processes for importing fully formed fault tree into the tool. Okay. Does that answer those questions, Clint?
That was fantastic. Thanks, Joe.
Okay.
Well, perfect. Thanks, Joe. I really appreciate you sharing, this overview of our fault tree tool. And like I said, if anyone has additional questions, I want to put our contact information back up on the screen there for you. Don't hesitate to reach out. We want to be a resource here for you. Coupled with, make sure to download the free demo. There's no obligation. You can download it, start playing around with the tool, let us answer questions along the way, and happy to help however we can here at Isograph. So once again, I appreciate everyone attending. Thanks, Joe. Thanks, Clint, and we'll go from there. Thanks so much, guys.
Thank you.